this video, we are going to discuss spring potential energy. But before we can discuss spring potential energy, we have to introduce the spring force. When we talked about gravitational potential energy, we already knew how to calculate gravitational force from the prior topic. But now we're introducing a new force. I told you guys we'd learn about more later on in the semester. Alright, so the spring force, represented by F with a lowercase s, is equal to K times X, where K is the spring constant with units of newtons per meter, so it's not a unitless number, and it characterizes how springy the spring is. So it's going to be a large value when it's a very stiff spring, and a very small value when it's a loose spring. And these numbers can vary anywhere up to hundreds of thousands, all the way down to just, one or two. So there is a wide range of spring constants, and this is something you'd either be given in the problem or asked to be solved for. This is not something you're going to come up with off the top of your head. And since it varies from spring to spring, it's not a constant value you can memorize. And X in this formula is the distance from equilibrium. So if you lay a spring down on its side, it has a natural resting place. And that's where X is going to be 0. So we would mark the end of the spring as being where X equals 0 is. And if we pull the spring back, X is going to equal some value, or if we push the spring in, X is going to equal some negative value because you've compressed it. So this is how you would calculate the spring force. Now my whole purpose of showing you the spring force is for us to be able to use that formula to find the spring potential energy. We are not going to solve any problems in this particular unit using the spring force equation. We'll revisit that concept when we get to the end of the semester in topic 13. So keep in mind, even though I've introduced this formula, because we're going to use it in a moment to derive the spring potential energy, we're not actually solving any problems in this topic or this unit using this equation. Now we know that work is equal to force times displacement. So naturally, we would just plug in the spring force equation and multiply it by the displacement. Now, I want to keep in mind I've chosen to do this in the x direction. The x in the spring force equation is the distance from equilibrium, regardless of whether the spring is horizontal or vertical. So it doesn't change if the spring is in the y direction, it doesn't become k times y. So x does not mean x direction in this case. Alright, so it seems natural we would take a horizontal spring and say k times x times delta x. But there's one issue with this. The force is not constant with displacement. The force due to gravity, the y value did not change what m times g equaled. But here, the x value changes what the Fs value, or force of the spring, equals. This means that we have to establish what the spring potential energy is in a slightly different way, because I have to take into account the fact that this value here is changing as this changes. And we're going to do this using a technique. Now, if you've taken a calculus class, you'll recognize what this technique is. But I'm going to introduce it here to those who obviously have not taken a calculus class, because that's not a prereq for this course. So we're going to plot force on the y-axis and displacement on the x-axis. And this is a linear relationship, since the force is as x to the first power. So we're going to get this white line here. And one way of finding work here is to find the area under the line. So that's why I've drawn this vertical red line down and shaded it in red. So essentially we're trying to find the area of this triangle here. And we know the area of a triangle is 1/2 base times height. The base here is going to be the x-axis, or the displacement. So what is the final x value minus the initial, and our initial is going to be 0. And the height of the triangle is going to be defined by the y-axis, or the force. So k times x final minus k times x initial, but the initial is going to be 0, because we're down here along the x-axis, or where y equals 0. So that means we get work equals 1/2 k x final squared, because I have to take this x times this x, minus 0, where that minus 0 would actually be the initial spring potential energy. So we get that spring potential energy is equal to 1/2 the spring constant times the distance from equilibrium, so how far the spring back has been pulled back or compressed in, and that value has to be squared. This now allows me to expand my conservation of energy formula. So we have here our initial kinetic energy, our initial spring potential energy, our initial gravitational potential energy, our work non-conservative. Remember, most of the time this term is going to be negative. And that's going to equal our final kinetic energy plus our final spring potential energy plus our final gravitational potential energy. Now it seems like there's a lot of terms in this particular formula, but keep in mind that you're not going to use all of them for every equation. So if you start from rest or you come to a stop, one of your kinetic energies is going to end up being zero. In fact, they both might be zero if you start at rest and end at rest. Your spring potential energy, obviously you're not going to use spring potential energy if there's no spring in the problem. Not every problem is going to have a spring in it. And the spring potential energy is going to be zero whenever the spring is relaxed back to its equilibrium position. So if you have a spring compressed initially and you release it, it transfers its spring potential energy to an object. It no longer has spring potential energy, so spring potential energy final is zero. Or if you start with the spring relaxed, so your initial spring potential energy is zero, and then you run something into the spring and it compresses, that's when you get spring potential energy. And gravitational potential energy, remember, you're always defining that relative to a baseline, and a lot of times then we make the ground zero. And so therefore, if you start at the ground, your initial gravitational potential energy is zero. And if you move horizontally, your gravitational potential energy is going to remain zero. Or you might fly up in the air, in which case you're then gain gravitational potential energy. So even though it looks like there's a lot of terms in this equation, you're not going to be using every single one of them in every problem.